Okay, this is the second video of two, and there's just two more problems from our test on April 21st. Both of them are BC series problems. And on this one, number 28, it was the other more heavily missed question that we had. So which of the following series converge to 2? So looking at these I guess, three, it to me is glaringly apparent that 2 and 3 are both going to converge. They both have an n in the denominator, raising to the power. They both have a constant up top, and pretty clearly, I guess they're going to converge, and it should be clear they're geometric. So on this one, on 2, we're starting with an n equals 1. So the first term in this series would be 8/3, and then the next term we're going to multiply by another 3 on the bottom, so we'd have a minus in there, and then we'd have the next term, if we put a 2 in, would be 8/9, and then the next term after that, we're going to multiply by a 3 again, we'd have 8/27, and it's going to keep flip-flopping, the common multiple being a -1/3, so that's our r, and our first term being 8/3. So then to check this thing, if it's geometric, we're going to say, okay, infinite geometric, 8/3 as our first term, and then we have 1 minus a -1/3 right here. So we've got 8/3 over, let's see, that would be 4/3. And then, let's see, we're going to flip. So we've got 8/3 times 3/4. The 3's cancel. And I've got 8/4, which is just a sneaky way of saying 2. So that means this one works. This geometric, this infinite series works. So it's either got to be B or it's got to be E. Those are the only two options that have a 2 in it. 3, the other infinite geometric, starts at 0. So this one, and then the first term is 1. I'll put a 1 in, and then I've got 1/2, and this one's all positive. And I'll put a 2 in, I've got 1/4, and it just marches downward in that fashion. Again, in this case, to do an infinite geometric, I guess I should have done the ... right there. We've got a 1 on top, and on the bottom we would have 1 minus a half, which would be our common ratio. So we have 1 divided by a half, flip the 2, and that one really quickly we can show is 2. At this point, we don't really need to check the first one because there is no option 1, 2, and 3. The answer ends up being E. That first one, though, and what makes it tricky is if you do the limit as n goes to infinity on the actual sequence, and again, I want to be careful with my language, on the sequence and not the series. In other words, the string of numbers. If you check what happens when n gets really big, in other words, as you get way out in the ... and as you're way out there, you're going to divide by the highest power, so it's going to leave us with a 2/1 plus 3/n. And we've got this limit as n goes to infinity, so now the infinity is going to go in. And we're going to end up with a 2/1, which is 2. That's what happens to the sequence. So that's like the end of the ... The thing that keeps happening then at the end is we keep getting 2's over and over and over again. The sequence converges to 2. The series does not. The series is actually divergent because it ends at a 2 value, or very, very close to 2. So that's like they throw that in there as kind of to trip you up with a series sequence thing. That seemed like our only stumbling block on it as a group, but I think important to point out and a really good reminder, memory jogger of what it means to compute an infinite geometric, which both 2 and 3 are. So our answer on this one ends up being E. And the last problem that we ran into some small problems with, this one wasn't as much, figuring out which of these series diverge. So trying to figure out which ones of these diverge. So in looking at this thing, let's see, we've got sine of 2, which is some number, and we're not going to know what number it is if we don't have a calculator, which this one wouldn't. But we know that sine of anything is trapped between -1 and +1. So this thing on top, sine of 2. Again, I don't know what it is, and you can actually go in a calculator and verify specifically what it is. It doesn't matter because that thing is being divided by pi, which we know is 3.14, which is bigger than anything from -1 to 1, and then we're going to take that to the n. So in other words, we've got this geometric where the thing on the inside is a fraction. And again, we're not actually asked to compute it, but that means that thing converges. So number one, we've got converge, which immediately factors out, let's see, if we're looking for divergence, boom, boom, and boom. And that's just kind of sight recognition. You wouldn't really even have to go through all this. And you're down to only A or D. So you're down to the D ends up being the right answer on this one. So 2 and 3 are the ones that work. Which means if you know it's either 3 only or 2 and 3 only, we can just go and check 2. And then if 2 works, we're good. And if it doesn't, we know we got to pick A. And you can certainly verify that 3 diverges. But to do number 2, 2 is a p-series. With the p being 1/3. And so that was one of the earliest on ones that we looked at. And if we have a p-series where the p is less than 1, or less than or equal to 1 because of the harmonic, that thing diverges. So that power has to be bigger than 1 on the bottom. It's maybe a simpler way to say it for it to converge. So that would need to be something larger than 1. Since it's not, it diverges. And based on the options we have left, it has to be D. Now you can go in there and do the analysis on 3 if you'd like, just to verify that, hey, yeah, this thing is gonna diverge. But in reality, we've got enough now to say we know what the answer is. And if we want to do the checking on this thing, the initial kind of way we oftentimes do it is we think about, well, what happens if you do a ratio test, or what happens if you send the limit to infinity. Those actually on this one are a little bit tricky, and this goes way back. The way you can evaluate this one goes way back to early on when we looked at these things and doing an integral test. Because it's a 1 to infinity, we can actually integrate from 1 to infinity this expression. So e to the n plus 1. I guess since it's n, this would be dn. I could change that to x, and that would be fine. To do this, I'm going to do u equals e to the n plus 1. And du is e to the n dn. So then we have this expression that would be e to the n dn would get knocked out by the du. We'd have 1 over u du, which is ln. So ln of u. And that's going to be ln of e to the n plus 1. We're going to evaluate that from 1 to infinity. It's not my best infinity. Infinity goes in. I get ln of e to the infinity plus 1 is infinity. So ln of infinity minus the ln of e plus 1, which is a number. Obviously, ln of infinity is huge. That's infinity minus some numeric value is going to give me an infinity. And what that means is, in an integral test, if the integral from 1 to infinity diverges, which this one clearly does, then the summation from 1 to infinity diverges. And so this one would also be divergent. Again, we didn't need to go through and verify that because of the multiple choice method of picking out the correct answer. And probably actually the AP doesn't intend for you to do it. They probably actually intend for you to save time on it. Knock out the first one, understand the second's a p-series, and just roll from there. But you can do it and certainly verify it. And that's it. That's the end of our most missed questions.